Hey everyone. So Josh Patterson, Director of AI Infrastructure, and I lead the engineering for RAPIDS. And I apologize for my voice. It is, as all of you know, really cold outside, and I'm from Atlanta, and I'm not really used to this, so just bear with me. Thank you.
Could you raise the mic just a little higher?
I'm short.
Is this better? Oh, much better. So I'm going to just quickly give the background and the inspiration for RAPIDS. When I first joined NVIDIA, there was an in-memory database, in-GPU memory database called MapD. And we could do sub-second queries that would take 10, 20 node Spark clusters a few minutes. We could do these sub-second. And then there was Graphistry, which we're demoing in our booth downstairs. And we could do these real-time visualizations of these very large graphs. So millions of nodes and edges. And so both of these things were doing things that CPUs just couldn't really do quickly. But if I wanted to pass data between MapD to Graphistry, and MapD's recently changed their name to OmniSci if you want to look them up, it took about 2 minutes of copying and converting data back to host, and then changing formats, and then moving it back to the GPU, and then reloading it and doing something else. And so this was really kind of painful. And so every time we wanted to go from one GPU application to another GPU application in the data science space, we spent a lot of time just writing glue code, moving data around, copying and converting. And so this was really the core inspiration for RAPIDS, is how can we just have everything communicate with each other seamlessly on the GPU? And so our goal for RAPIDS is to really just do this, just reduce mem copies. It's something very simple and trivial, but as we started this process, what we realized is there were a lot of other things that were missing in the data science ecosystem, and it's quickly expanded to more than just reducing mem copies and creating common data formats. At the same time, as we were starting RAPIDS, Wes McKinney and others were starting Apache Arrow. So Apache Arrow is a in-memory common data format, and it's language agnostic. So Apache Arrow has Java, JavaScript, C++, C, Java, sorry, I already said Java, Python, Rust, Ruby, and I believe Go bindings so far. So it's about 8 to 10 different language bindings. But what we also realized about Apache Arrow that was really unique is it was also hardware agnostic. So it could run on the CPU or the GPU. And so we would just have to copy data. So there was no more of this conversion. And most data scientists spend a lot of time when you're thinking about systems just serializing and deserializing data and copying it between different formats for usability. So Apache Arrow really gave us this nice representation of data that was very agnostic, so we could use it in many places. And this is really the backbone of RAPIDS. So the inspiration of RAPIDS was to reduce mem copies. The backbone of it is Apache Arrow, essentially having this one representation that everyone agrees on. So normally I talk more about data growing and why GPUs are great, but I'm assuming I don't have to do that for you all. So I'm just going to jump straight into RAPIDS and talk about the platform, where we are today, where we're going, and just kind of some of the performance improvements we're seeing so far. And so RAPIDS is our end-to-end open source data science ecosystem. Essentially, it has an analytics library for just tabular data manipulation, a machine learning library, a graph analytics library coming soon, and integration with certain deep learning frameworks, and we're going to continue to expand those, as well as integration into visualization libraries. And so the top half of this slide is actually a slide that was from Spark. And so it really inspired kind of a lot of our thoughts around this. And so when we moved originally from Hadoop and MapReduce to Spark and memory, one of the biggest improvements was usability plus leaving things in memory. When you leave things in memory and you're not reading and writing to disk, you get a lot of improvements. The early GPU data science world, which is, has its roots all the way back to 2011, 2010, probably earlier than that, what we noticed in a lot of the literature is there's a lot of just copy and converting data. And so a lot of the argument was if there wasn't enough computation, the speedups weren't as large. And so people would really kind of relegate GPUs for data science for only really large computationally intensive problems because of the memory copy penalty. And so if you just want to do kind of arbitrary data science on GPUs and you had to copy and convert between these formats or copy back to host memory often, you were only really seeing like a 5 to 10x benefit, and sometimes it wasn't worth it with the increased rigidity of languages and coding. But one of the things about RAPIDS is we want to make it very simple to use, plus we want to reduce the mem copies. And so, we have a lot of Python APIs directly to the underlying CUDA C++, which allows us to get this pretty large speed up, as well as we can do things that traditionally were a little bit more difficult because we leave everything in GPU memory. So normally people leave this to the end, but being one of our newer open source projects, I just want to quickly talk about how you can get started. So we have containers on NGC and Docker Hub. On GitHub, we have source code, and right now you can conda install. I believe we're at 0.3 for both KuDF and QML, and we'll have pip install by the end of the month. So I'm just going to double click into two of the libraries quickly, and then talk about KuDF in a few minutes. So on our machine learning side, I know most of this conference, it talks about deep learning and neural networks, but I think machine learning is really important because there's just certain problems, where there is, some advantages, whether it's computational time or setting a better benchmark by just using machine learning. And so I think there's kind of no free lunch where we always need different types of models for different types of applications, and so they all should be accelerated. And so while we have historically focused on deep learning, we're kind of expanding out to more just general machine learning as well. So today we have within RAPIDS accelerated decision trees, Kmeans, KNN, DBScan, PCA, and SVD, and then we're going to continue down the list to fill in the gaps that we have currently. So we should have more algorithms coming out in the next month, as well as early next year. Graph analytics, we spent a lot of time with graph analytics and NVGraph. One of the major complaints of NVGraph, though, was the usability of it. It was a pure CUDA C++ library. So we're doing exactly what we did with machine learning. We're adding Python APIs. We're making it where it can accept an Arrow data frame directly into the graph analytics library, do all the conversion on the back end, and basically be more like NetworkX is to the PyData community or GraphX is to the Spark community. And so just a quick benchmark, comparing a dual socket system, so 40 cores to 8 GPUs on a DGX1, we saw about a 90x improvement. Most of our machine learning models we're seeing somewhere between 10 to 20x socket to GPU. And then as well, we're spending a lot of time thinking about time series because that's kind of very core to a lot of our enterprise customers, as well as a lot of economists spend a lot of time thinking about things in terms of time series. And so giving my econometrics background, even though time series sometimes gets not as used as much, I think it's a very important part of just kind of traditional data science. And so we launched RAPIDS about a month ago, on October 10th in Munich. And this was kind of our flagship benchmark. And so to talk a little bit more about this, this is a 250 gigabyte problem. So we're loading all the mortgage data from Fannie Mae from 2000 to 2016 into GPU memory. And we're loading it directly from disk to the GPU. We're doing some processing on it. Raise your hand if you're familiar with mortgages and how they operate. Okay. It's actually amazing. Different crowds, either you see the whole room or none of the room. And so I'll quickly explain how mortgages work. When you have a mortgage, you have certain characteristics of the borrower: number of borrowers, credit score, debt to income, so how much money you make versus how much debt you have. And there's a long list of things that they care about: what zip code you're buying in, what are the neighboring zip codes' effects on that zip code. And so they do these kind of large machine learning operations based on your credit characteristics plus the characteristics of the house. And so that's how they decide if you should get a loan. The next thing is, as a mortgage broker, you care about when you're buying loans. You buy portfolios of loans, you trade them. They're called mortgage-backed securities. When you're buying these large securities of loans, the goal is to buy loans that will pay for a very, very long time. You don't want to buy a loan that you think the person will default on, and you also don't want to buy a loan where you think the person will prepay. And so it's a little counterintuitive. You would think that banks want you to prepay your loans. In fact, they don't. They want you to pay and pay for all 15 or 30 years. And so we have these two sets of data, basically your payment history and the characteristics of the loan and the borrower. And so we basically do a bunch of group bys and joins to merge these two data sets together in a meaningful way to build a training data set. And with this training data set, we basically want to then predict out what will happen to this loan in the following year. Will this loan at any given month default or prepay in the next year? And we basically do a binary classification. Both of those are bad events, so those are 1, and 0 is the loan continues to make payments. And so the very thin blue is the ETL time. So basically loading this 250 gigabytes of data from CSV into GPU memory, doing all the pre-processing. The orange is it's essentially converting the data into some representation that's usable by a machine learning library, in this case XGBoost. And then the gray is the machine learning time. And so as you can see, the DGX2 basically does all of this a lot faster than even a scale-out system. And we're using AWS R4.8x extra large instances in comparison here. And so the same workflow, but now we're comparing a DGX2, so 16 GPUs versus 5 DGX1s, 40 GPUs. But the difference here is one are fully connected by NVSwitch, the other one has to go out to network. And so we still see this kind of somewhat close to linear improvement on the ETL side, mainly because it's embarrassingly parallel. We basically do the whole ETL process in memory in one pass, whereas machine learning is a little bit more complicated. And once you have to start going out to network, you lose some of these performance advantages. So this is actually one of my favorite slides. Same benchmark, but we actually reduced the data set down. So we're only looking at 40 gigabytes of data here roughly. And so this is enough where even with the kind of explosion of data during some of the ETL steps, we can still fit the data in GPU memory. And so this is essentially a DGX station, so 4 32 gigabyte GPUs versus 5, 10 to 25 Spark nodes. And what you notice is there's no data prep time. In fact, there is some data prep time for machine learning, but it happens so quickly. We're talking microseconds. Essentially, it's just not there because changing data formats in GPU memory, if the data never has to leave the GPU memory, is very quick. And so this is kind of where we want to fully go. So think about large-scale distributed systems where you can do all of your ETL in GPU memory and your machine learning. It really reduces your total computation time. And this is the last kind of XGBoost benchmark. This is just showing the difference between scale out and scale up with the DGX2 versus the DGX1. There was a paper in 2016 about better communication in gradient boosted decision trees at NeurIPS. And some of those methods were actually going to integrate into XGBoost proper. And so we should be able to reduce some of the 5 DGX1 time by just better communication protocols. But still, you're only seeing about a 5% benefit today. Hopefully we can increase that. But it really shows kind of the benefit of an NVSwitch, mainly because it's almost like having locally 400 gigabit Ethernet just within a box versus having only 100 gigabit going out. So a few more machine learning benchmarks, TSVD, PCA, and DBScan. We're basically just comparing these to scikit-learn, single GPU to a single socket. And you're seeing some pretty significant speed-ups. Some algorithms are better than others. And the point of this is we're going to go through the whole ecosystem. Some currently are multi-GPU, multi-node. Some are single-node, multi-GPU, and some are single GPU, like these algorithms. But over time, we're going to continue to scale these algorithms out. And so last month, we added in Kmeans. So that is single-node, multi-GPU, as well as we integrated with Facebook's Face, so their approximate nearest neighbor, KNN. And we're adding in common filtering, collaborative filtering, GLM, and random forest in the next couple of months. And then early next year, as I said earlier, some of the time series, the ARIMA, Holtz winner, and there's this really great dimensionality reduction algorithm, UMAP. Just been really impressed with the work of Leland, and it's kind of a newer algorithm that is been talked a lot about at SciPy and some of the other PyData conferences, and it's really just KNN with a stochastic gradient descent. So we're going to add this into our library just because we have the right building blocks for it, and it performs very well compared to some of the other traditional dimensionality reduction algorithms, as well as some Bayesian methods. And so just a little bit of a teaser. So we actually will have KuGraph next week integrated into RAPIDS in our 0.1 release. And so we're going to start with PageRank. Surprisingly, NetworkX is very well downloaded and used in the PyData ecosystem. So when you looked at pip and conda installs in aggregate for NetworkX, a graph analytics library, we saw that it was roughly proportional or slightly higher than the number of TensorFlow downloads, which was really surprising for us. And it's a graph analytics library that's fully written in Python. And so there's some performance issues, but the usability is really high. And so given that all of RAPIDS follows the same kind of paradigm, CUDA C++ with Python bindings on it, we're essentially mimicking the NetworkX API, but using NVGraph and other graph analytics libraries under the hood. And we're getting these 2 to 3 orders of magnitude speed up. And so we're going to systematically go through all the graph analytics libraries as well and make sure that they're single node, multi-GPU at least, and for some exploring multi-node, multi-GPU as well. And so now I'm going to talk about my favorite part of this, which for some people is the least interesting, but it's just a DataFrame library, KuDF. I love this little kind of infographic. One of our data viz data scientists basically sketched out, kind of what a day in the life of a person is before and after GPUs for data science. So I'm going to go ahead and just click to the next slide real fast. So most people spend about 90% of their time just doing data processing, cleaning up data, making data usable for these experiments. And I just thought this was a really kind of great way of thinking about it. I know when I was at Freddie and Fannie, we would kick off these large-scale kind of hyperparameter searches. And basically, you knew that after you did that, the rest of your day was coffee, donuts, and kind of hanging out at the mall, waiting for that email saying that you're close to being done. With this, the iteration times are a lot faster, so it really kind of keeps people a little bit more engaged. But yeah, so I think this is just kind of a really great way of thinking about what's the importance of time. If you have these, as researchers, your time is very valuable, and so if you are out of compute resources and you're just sitting around waiting, essentially you're not progressing your research, you're not finding any better answers. And so the whole point of RAPID is really kind of accelerating the whole end-to-end pipeline. So KuDF is exactly what it sounds like. It's a CUDA DataFrame library. It's Apache Arrow under the hood, like all the other parts of RAPIDS, and it does basically what Pandas does. It's about 95% compatible with the API. We work closely with the Pandas community in West McKinney, and there are certain things that essentially we know where Pandas 2 is going, and certain parts of Pandas will get deprecated out. So there was no reason for us to go backwards. So it's Python 3 only, mainly because Python 2 is getting close to end of life. But it basically tries to mimic the Pandas experience, and it's a highly Pythonic library, but it just does, data pipeline things, joins, group bys. And I'll talk a little bit more about strings a bit later, but this is kind of the core backbone of data science. And this is, I think, probably one of the more painful parts. When you have these 20 gigabyte to 1 terabyte data sets, it's really kind of this no man's land. Once you get above 1 terabyte, Spark obviously becomes the right thing to do. But and Pandas falls off after about 20 gigabytes where it's just unbearably slow. But between those two things, which seems like a very large range, there's really just not a great tool. And so these data sets can now fit fully in GPU memory on single nodes, and we can just process a lot quicker. So how it's built, just similar to everything else. CUDA on one side, we've open sourced all of the low-level libraries, all of the CUDA implementations for our hash-based group bys, our hash-based joins, our sort-based joins, all of our element-wise operations. And then we use Python to bind to that CUDA C++ to have the simple-to-use Python API. A lot of data science, though, are these kind of complex where and if statements, case statements. And so we use Numba to do JIT compilation for these user-defined functions. So we have full user-defined functions support, and it still runs fully on the GPU. And so similar to the PyData ecosystem, Pandas is a single core library, and you can use Dask for parallelism of this library. We use Dask as well. So we think of a GPU as a single worker, and we scale out with Dask. And so with Dask, we use it both on the machine learning side and the data frame and graph as well. And so Dask essentially acts as our scheduler. Dask is really great because it has no restrictions on the compute side. And so the scheduler is fully independent of the compute. And so it was actually very simple for us to replace out the CPU computation engine with a GPU one. And so some of the things that we did with Dask to make it a little bit better, though, pickling data is really painful. I think most people have some experience with pickling data. And when we're talking about pickling hundreds of gigabytes of data, that's probably a bad idea. But what Pickle does, though, is it's very extensible. And so we said instead of pickling data, we're actually going to pickle CUDA IPC. And so what this does is because we have this nice mix between CUDA and Python, we actually don't move the data through Python. We just say, hey, I want to move this data, so I'm just going to pass this pointer to the data. And then Dask passes that to the other GPU, and then the GPU resolves it. So then it still can leverage all the benefits of NVLink, RDMA, and other types of hardware acceleration without actually going across the socket. As well as we're integrating Dask with OpenUCX so we can have this more MPI-like communication for multi-node. Okay, and then on the machine learning side, essentially we didn't want to reinvent the wheel. And so because Dask has essentially a block scheduling, it can basically hand off and say, all right, I'm done. I'll allow this other process to do its communication and its different collectives. It was actually really simple to integrate Dask with Nickel, and so this is what we did with XGBoost. And so XGBoost uses Nickel too. What Dask does is Dask actually, it does all the handshakes for the communication ranks, and then it says, okay, I'm going to pass this off to Rabbit, which is the XGBoost communication, which then uses Nickel under the hood. So even though it's a tiered communication approach, basically Dask is hands off while XGBoost is running, and then as soon as XGBoost is over, it continues on with its directed acyclic graphs and other types of scheduling. So quick look into the future. We're going to continue to improve performance on single GPU, multi-GPU, and multi-node. Strings are very important. I'm really excited to actually be able to finally say that strings will be out next week. The string library is something that we haven't had in CUDA. It's actually something that a lot of the more parallel analysis libraries just don't have. Even Numba just recently added support for strings in 0.41, which was last week. And so if you wanted to do strings in parallel, there wasn't really a good option. And so just a quick look at some of our string performance. If I want to find a substring in a string, we're doing that about 40x faster on GPUs, slicing, lowering. One of the interesting things that and we're still very early in our string performance, we're finding that if we sort the data by character length, we actually get more performance with the GPU. And so we see almost a 20 to 30% boost in some of these operations. And so we're still trying to figure out what's the best way to represent strings, what's the best way to process strings. But we basically want to iterate and learn with the community. So we're going to release KuString next week, and we have a blog coming out about how to use it, how to integrate it with our DataFrame library, or how to use it completely independent of RAPIDS if you so choose. Another thing that people are really excited about are just basically importing data. This sounds somewhat trivial, but I didn't realize that there was a CSV conference. There was a whole conference dedicated to CSVs, how people interact with CSVs, how people can accelerate CSV loading. People actually spend a lot of time thinking about this, and there was actually this really great paper from Airbnb about moving from decision trees to neural networks for predictions and recommendations. And they said when they first did this, they were only getting about 10% utilization on their GPUs because they were trying to bring all this data in from CSV. And I think quoting the paper, they said it was like pulling a Ferrari with a mule. That was what they said, not me. And so in some of our early customer experience, we've seen almost a 10x improvement on deep learning jobs by using the CSV reader plus TensorFlow. just because you can load data a lot faster. And so here's the Apache Cradle benchmark of loading different data formats. But basically, you're limited by the CPU at a certain extent, and we're basically getting NVMe speeds for loading CSVs with our CSV reader. In the next month, we'll have Parquet and Orc readers out as well. Then finally, how do we integrate with deep learning? So we have a tight integration with Chainer coming out in the 6.0 release of Chainer. The pull request was fully accepted. And essentially, you have bidirectional communication with Numba. So we use Numba to cast an Arrow data frame as an array or a tensor or whatever representation you would like. And then Chainer, KuPy, can read this in directly into their deep learning framework, as well as push data back through Numba into KuDF. And we're working on the same with PyTorch as well. So that's it. Very early stage in this project. The best way to improve projects is to get issues, feedback. We love pull requests if you want to donate code as well. So that's it for me. Thank you.